My name is Bill Karwin. I thank you very much for inviting me to speak today. I'm going to talk about SQL injection today, and we're going to go pretty far in depth to this. This group probably knows quite a bit about it. This talk is usually targeted toward developers, but either you'll find some things in here that's interesting to you, or you will find some good arguments to use with your developers to get them to go on the straight and narrow. I've been a software developer for about 20 years. I've also been answering questions on SQL-related topics for about 15 years. Way back in the dawn of time, I worked for Borland on their Interbase RDBMS product, and I was doing technical support and training and writing the documentation for that product until about 1999. After that, I was using MySQL. So I've been using MySQL for about 10 or 11 years now, and spent a lot of time on the MySQL forums, several years there, answered a few thousand questions. And from there, I started becoming really a fan of Stack Overflow. So you may see me on Stack Overflow answering a lot of SQL questions. I think I'm the only person with the badge for database design, on earning enough points through database design on Stack Overflow currently. And last couple of years, I've been writing a book basically collecting all the most frequent questions that I have answered over the years on SQL topics and doing a thorough treatment of each one of them to try to identify the sort of heavy hitters or the common blunders that people make with their SQL development. The book is also targeted toward developers, and that's now come out this year in about June, and it's doing rather well. Very happy with that. I'm actually thinking of doing another one. So what I'm going to talk about today is SQL injection, which is a security topic. And as I researched this topic, I started to realize that a security topic like SQL injection is perhaps the #1 thing that every person responsible for a database or a database-driven application should educate themselves about, even before things like data modeling and performance. Because the implications of a flaw in a security model are pretty dire. And I'll talk about that in a couple of minutes. But first, let me identify what is SQL injection. Probably most of us in this room know, but just so we're all on the same page, when we program in dynamic SQL, that is, we're preparing a query to run as a string, or a string to be interpreted as an SQL query, we often find that some of our application data, some of our logic and variables in our application code needs to be interpolated into the string of the query and then executed at runtime. This is distinct from the really old days when static SQL was part of applications, and you would use a precompiler to generate the code for that. But it's pretty much de rigueur today to use dynamic SQL. And here's an example of using PHP to interpolate a request variable directly into the string of your query, which we get from user input directly from a web application parameter. And the problem with this, as we've probably all seen, is that sometimes the format of that input can be something that we didn't intend. It can be something that either by accident or by malicious attack has introduced new content into your application and resulted in the query running in a way that you did not intend. So what about this example? In this case, somebody was clever and they modified the format. Instead of just being a simple integer, they allow a whole SQL expression, which when interpolated into the query changes the condition that the query applies to. And now we're going to read every row from our database table instead of just the one that corresponds to the primary key that we were looking for. So that's clearly not what we intended, but maybe it's not so bad. We get more rows instead of just one. But let's take a look at a different example where we're doing updating of data. If we have a couple of variables that get interpolated into this update statement to change my password, I'm going to use both of these assume both of these variables came from request input in an application, and one of them has a quoted string that we don't know what the content of that is, and the other one is supposed to be an integer. So what could go wrong here? Well, somebody could cleverly form the content of those request variables and do two things. One is they can form the updates so that you're setting two columns instead of just one column, and they can also make this apply to every row in the table. So what would this do? It would set me, not only change my password, but it would set me to an administrator role for this account, and it would apply to every row in the table. So with this type of attack, I could manipulate your application into making me, not only me the administrator and changing my password, but changing all the account's passwords so that I can log into any account. These are just two different examples. Either one of them would be bad, but that's what I mean by SQL injection. Again, sometimes this is by accident. Sometimes it's not an intentional attack on your application. It's just somebody formed an input that was not what you expected. It isn't a simple integer, or it has a quote in the middle of it, which upsets the string termination. But if it's an accidental error, it's more likely just to generate a parse error than something malicious and clever. It does happen, though, that hackers who are trying to gain illicit access to your account can do this cleverly and break in. Okay, so that's the foundation. That's sort of the what is SQL injection. So how do we defend against this? This is our responsibility as developers or database administrators to try and find out what are the ways that we can defend against this. And I see a lot of people suggesting fixes for this. And I'm going to try to address a bunch of the comments and observations that people have about this condition or SQL injection threats, and phrase them in terms of here's what people say, and here's the relative merit, the truth or falsehood of it. So one thing you might hear, SQL injection, that's been around for years. That's an old problem. Somebody must have come up with a fix for that by now. Well, in fact, it's such an old problem that it's a favorite problem of hackers. And the big example that happened a couple of years ago was that a man named Albert Gonzalez used SQL injection to hack into ATM systems at a number of convenience stores in order to upload some malware that he wrote to monitor network traffic. And what's a network traffic in an ATM system? It's credit card numbers and debit card numbers. So he was capturing authorized credit card numbers and their PIN numbers at an ATM system, saving that off and shipping the data off to some colleagues of his in Russia. And he broke the record of most credit card numbers stolen in this way, tripled the previous record, in fact, which he himself already was the perpetrator of. So he's going for a personal best, I guess. So he did this in 2007. He was sentenced for 20 years in March 2010. An example of the impact of this is one of the victim companies had to pay upwards of $12 million to fix this problem, just for fines and to compensate people who had been victimized. Then on top of that $12 million, they had to fix all of their code inspections and rewrites and redeployments and so on. And they were only one of the victim companies of 2 or 3 companies. Other cases of SQL injection, these are by no means exhaustive, but these are just ones I picked out of Wikipedia. But clearly, 2008, 2009, they're still going on. And the impact is pretty dire. In the thousands, tens of thousands, millions of compromised records of your database that perpetrators of SQL injection can gain access to. And Verizon Business Risk Team did a report on data breaches and found that SQL injection is probably the #1 or #2, depending on how you count it, method for breaking into databases, and it accounts for the majority of the actual data compromised. So clearly this is still an ongoing problem, and we have to be aware of it. So what do people do to get around this, to defend against it? One answer you often hear is escaping input prevents SQL injection. That's probably the most frequent solution that people have, and I'll show you an example. If we were to have our update statement that I showed earlier, but we were just conscious of the fact that the string that we interpolate into that query could contain a mismatched quote character, and we make sure to escape that quote character with a backslash. And likewise, when the where clause needs to have a dynamic integer interpolated into it, if we make sure that that input is only an integer by stripping off anything that doesn't look like an integer, for example, or coercing it by data type. In PHP, for an example, there are functions to do this that are built into the API methods for MySQL. MySQL real escape string does that. Any text that you hand that, it'll come back in a form which is safe to interpolate into a quoted string. And the other example I use here is a typecast to make sure that the other variable is coerced into being a simple integer. So if you prefer one of the other MySQL APIs in PHP, like PDO, there are similar functions there too. The PDO one is nice. I like that one because it actually puts the quotes on to delimit the string as well. So, sounds great, right? This is an effective defense against those types of interpolating dynamic variables in. What about other cases? If you want to do a query that treats as dynamic the column by which to sort. So you want to have an order by clause with user input to determine which column is going to be used for the order and whether it's ascending or descending. What do you do there? Well, it turns out that those APIs don't have a function to escape the content that gets interpolated into a delimited column name. Columns are delimited by backticks in MySQL or double quotes in ANSI SQL, but that means you have to put a backslash in front of backticks or double quotes, and the escape string function doesn't do that. And likewise, if you are interpolating dynamic application variables into your SQL string that need to become treated as SQL keywords, like ascending or descending, those don't have delimiters at all. There's no backticks, there's no single quotes, there's no double quotes. They have to be bare words in your SQL string. So how do you protect against that? And there's no way to ensure that that is escaped. It doesn't make any sense to try to escape that because you're not finding any quotes to imbalance or any backslashes and so on. So although escaping the strings is helpful, it doesn't account for all these cases. Another thing that I hear developers say a lot is, if some escaping is good, more must be better. This sort of goes along with the general American attitude toward the economy. So you see things like this. So they said, well, MySQL real escape string was good. I'm going to wrap that around my password. But there's all these other functions in PHP that do similar things. I'm going to use them all because more defense is better, right? Well, now you end up with backslashes or before your backslashes and things encoded in HTML entity tags and so on, which is totally inappropriate for inserting into the database. It makes no sense in SQL syntax to have ampersand LT semicolon, which would be a good defense if you were outputting this to HTML output from a web application, but makes no sense if you're trying to encode something in an insert statement or an update statement. What I think when I see developers post code like this is the scene from the recent Star Trek movie where the villain says, "Fire everything!" at the Enterprise. Like, if one thing is good, then the rest must be better. And I have to tell them, just use the function that is intended for that purpose, that's enough as long as you use it consistently and it's the appropriate function to use. Okay, moving on. What else do you hear? I can write my own escaping function. Why is this a myth or a fallacy? People say, well, putting backslashes in front of things is something I can do with a regular expression replace function. That's pretty ordinary, right? But it turns out that one of the attributes of a MySQL connection to a database is a character set. And you can have multi-byte character sets. And you get into situations that are a little esoteric, but do occur, where a backslash followed by a quote character can be interpreted as a multi-byte character in the character set that you're using, which can now mean that you have, again, imbalanced quotes. So something simple like add slashes, which is not aware of the character set that you're using, may seem convenient for a developer to use, but please don't do that. It's not character set aware. I have a couple links in here that are too small to read on the slides, but you can follow them later when you have access to the slides that go to blogs that explain in excruciating detail the way that this actually works. And it's not necessary to use these. You don't need to write your own function. You can use the functions that are provided in the API for MySQL. Every language and every library to access MySQL has something like this, the MySQL real escape string or an equivalent. And those do go back to the MySQL client to get information about the connection character set, and it does the appropriate thing. So no need to reinvent that wheel. All right, next up, something I hear, well, unsafe data comes from users. If I've already taken care to make sure something gets inserted into my database safely, then it must be safe for subsequent use in an SQL statement. For example, if I'm doing a full text search looking for mentions of a given product in my bug database, for example, I might fetch that product name in one query and then interpolate it into a subsequent query to match it. But what if the name of the product itself contains a quote or other special characters? You could run into an SQL injection problem inadvertently here, or deliberately. Somebody may have logged a product name deliberately containing mismatched quotes and SQL syntax, hoping to do this kind of onesie-twosie attack. It seems a little far-fetched, but it actually does happen. So in this case, it would have been adequate to use, again, MySQL real escape string to make sure that that product name, even though it was safely in the database, gets treated as though it is untrusted input in the subsequent second query. Next up, a lot of people say, just use stored procedures for everything. That's a gateway that will create a secure situation for you, and there's no way anybody can break through that. Well, it is true that in a stored procedure, the SQL queries are more or less static. You can determine the query syntax at the time that you write the procedure, and you also have situations where a input goes through effectively a coercion to a data type, because you can only have integers come in if your input parameter is an integer. So it should be safe, right? Well, you can also do dynamic SQL in stored procedures. You can use prepare and execute and start concatenating together strings and create an unsafe query inadvertently. So in this case, I may want to, again, have my order by column be dynamic. So the column name and the ascending versus descending is determined by a string, which comes from I don't know where. And then as I execute that in my application, I can interpolate unsafe input from a user request or some other source, which the procedure doesn't know how to defend against. And you get SQL injection that way. There's even a great article on the Daily WTF What happened was a database administrator had a policy that everything must be gated through stored procedures. And if you need a new type of query, don't run the query against the database yourself. I haven't given you privileges to do that. Tell me what your query is. I'll write a stored procedure, and then you can do that. Which worked, except the DBA was a little annoyed at having to write new procedures every day for subtly different types of queries. Until one day when he finally said, well, I'll just write one query which dynamically interpolates the table name based on the string parameter of the procedure. And then you can query star from any table that you need to query from. Suddenly his phone calls went away, and he was happy. Because the developers figured out that they could pass a derived table in a parenthesized subquery, and it would get interpolated into the procedure, and that way they could query any table that they wanted. So they didn't have to bother the DBA anymore. He was happy. They got to do anything they wanted with the database. They were happy. But here's a prime case where, as they constructed this string in their application code before sending it to that procedure, they can make mistakes and interpolate unsafe data into their subquery, which they then go in. And nobody would know because the DBA says, well, I'm not getting called anymore. I can go home early. And the developers don't know how to defend against the risks of SQL injection, so they're happy and nobody ever does a code inspection. Okay, next thing we hear is, well, everybody knows how to use grant and revoke. Just make sure that you haven't granted too many privileges to applications that don't need them. So if we don't let an application do an update against a given table, that'll mitigate the damage that can be caused. But what if I, as an attacker, can manipulate your application into running a query like this, doing a Cartesian product against, I don't know, the same table 6 times over. So if you had 100 bugs in this table, now you've generated a result set of 1 trillion rows. And I'm feeling especially mean, so I'm going to throw an order by 1 on the end, causing a temporary table in your temp space to sort those 1 trillion rows. So it doesn't necessarily give me access to steal your data, but I can certainly do a denial of service attack that way. I've even seen examples like this, where a request literally has verbatim SQL, a complete query, as a visible parameter in the get URL. So quite easy to manipulate that if I'm an attacker. What about another one? Well, this application is just on the intranet. We're not going to have malicious attackers. Everybody here in the company is trusted, and they won't do that. They won't change the request parameters of this intranet application. That might be true, but eventually you find yourself working for this guy, and he says, yeah, I'm going to have to ask you to open up that application because we have some partners who want to have access to it, and just punch a hole through our firewall and let people run that application from outside, which you can understand that if you haven't constructed your application carefully with SQL injection defense in mind, would result in a problem. Or if you don't open up the firewall, but somebody says, wow, you coded that application so well, I'm just going to copy a little bit of your code and put it into this other application which is outside the firewall, and hence get myself in trouble that way. Code reuse, it's a good thing, right? And the problem is, the real defense in those situations is if you are asked to take some code that is not architected for safety and put it outside your firewall where it could be attacked, you say, well, we need to do a code inspection and it'll take 6 to 8 weeks to finish that. And the boss says, no, 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 that's too much expense, just get it done. We have to make this accessible by our partners by 5 p.m. today. Next thing I hear, I use a framework. I use Ruby or PHP or Python, and the framework takes care of all my SQL injection defense. It's all taken care of. Or an object relational mapper. But every object relational mapper library or framework that I've used or seen allows for exception cases where the framework doesn't handle some sophisticated or corner case of SQL. So their solution is, well, we'll just let the developer pass a fragment of SQL that contains verbatim logic. And that's where your SQL injection can get in. Anytime you can have a developer who is writing a string, which then gets interpolated into an SQL query, you can get into trouble. And what I realized is no framework and no library can take care of you all the time. One user came up to me after one of these presentations and asked me, can the database framework that you're using prevent SQL injection? And I told him, the framework prevents SQL injection like a toothbrush cures cavities. You have to use it consistently and correctly and make sure that you know what you're doing. But a framework can give you tools and convenient methods if you use them. But ultimately, it's your responsibility, and that's why I'm giving this talk, is to try to reinforce that the developer is responsible for application security. No framework can do that for you all the time. Okay, so what's next up? What's the next defense that we can use for SQL injection? Query parameters. This is the other thing that I hear or see in articles and blogs. Just use query parameters all the time and you'll be protected. What am I talking about here? Well, I've used the word interpolating when we actually copy a string into a string to form our SQL query. And this is a typical way of using an application. What developers then learn as they get more seasoned is that you can use what's called a parameter, which is a placeholder in your SQL string in lieu of the dynamic value from your application. And then subsequently you can provide the value to in place of that placeholder. Let's go into a little bit more detail about this. So this is how the RDBMS might look at your query after it's decomposed it into its syntactic elements and the optimizer of the database. It's broken down into the different clauses of the SQL in abstract syntactic elements, and then mapping directly to the literals that you had or identifiers that you had. And you can see the yellow bubble at the bottom, that's where the query parameter belongs. And it says, I know what a query parameter is. I'm going to record that in my parse tree for later inclusion because I know that the user is going to provide me a value before I have to actually execute this query. And when you provide the value, then the database says, substitute that value in, just in that little yellow bubble, and it'll execute it as though you had interpolated it from the beginning. But it's better than interpolation because if you were to use interpolation, what happens is it goes into the database before the parsing occurs, and hence the database says, well, the tree must look like this. The parse tree must look like this because that's the string I got from your user input. But it's a different shape now. This is how SQL injection modifies the logic or the semantics of the query by changing this shape of this parse tree before it gets to the database. If you had used a parameter, the parameter belongs in its own little bubble that gets determined as the database parses it, and no matter what value you give it subsequently, it knows that that's only one syntactic element in that parse tree, so it cannot break outside that. It cannot modify the size or shape of the tree. And therefore, it can't modify the behavior or the semantics of how it runs that query. Let me show this in a different way to go over it in a sequence diagram. If you have a client and a server, a client is an application, the server is your RDBMS, and you do a prepare of this query, including the parameter placeholder, the question mark that I showed. You send that SQL string to the server where it gets parsed and turned into that internal representation with the knowledge that part of it is a placeholder. At that point, the database can say, okay, I'm going to, now that I know which tables you're accessing and how you're sorting and doing all these other things, I can optimize. I can decide in what order I'm going to access the tables. I can decide which indexes are going to apply to your query, and I'm going to keep note of that. So all this detail given, this is a way that we can think of query parameters as being better than interpolating dynamic variables into our SQL strings, in that we don't have to do escaping, we don't have to worry about encoding issues for different character sets, we don't have to worry about coercing data types. We know that nothing a malicious or accidental input can do can change the semantics of the query that we run. So it sounds good, right? This is why you see people on blogs and magazines say, query parameters, just use them all the time. So they say query parameters prevent SQL injection, full stop. But there's some other cases. Because one parameter in the SQL language corresponds to one value. You can use a parameter in a place where you could otherwise have used one literal value and nothing else. So, for example, you can't do it in a place where you would use multiple values, like in an in clause, where you would have a comma-separated list of individual integers. The one parameter would allow you to put in a value, but it would get mapped to one value in the query. It would not be equivalent to having a string of values. You can't use a parameter to substitute for a table or any other identifier like a column. Again, these parameters can substitute only in a place where you would normally use a single string literal, an integer, a quoted string, quoted date literal, and so on. And likewise, it cannot be substituted for an SQL keyword. Back to summary, the different cases where you might use a dynamic portion of your SQL, trying to substitute for a single value, there you can use either interpolation or a parameter. Multiple values, you can have a string with integers and commas in it, for example, and interpolate that into an SQL string. But if you needed to use parameters, you would have to use one parameter placeholder for each value in your list. When your list could be of variable size, so you might have to use some built-in functions to your application code to decide how many question marks to put in there and then match that to the length of your list. But table names, column names, and other keywords, for example, whole expressions or SQL keywords, you can't use query parameters for those. So what do we do? Well, the solution that I use is, I call it Whitelist Maps. And I have an example in PHP again. Say we had our variable sorting query that I showed in the examples earlier, and I want a couple of web parameters, order and dir for direction, to indicate how I'm going to do that. The SQL injection way would be to just take the inputs directly out of my web request and interpolate those into the SQL query. But that, as we've seen, results in an SQL injection vulnerability. What I would rather do is make sure that those are valid inputs for the given query before I interpolate them in. Again, I can't use parameters because these are table names and SQL keywords. So let's take a look at what I do. I have a couple of associative arrays in PHP. The keys of the associative array are going to be the values that are given on the request. The values of the associative array are the actual values or portions of SQL syntax that I'm then going to interpolate into the query. And I have some defaults at the end in case those parameters aren't specified on a given request. So how do we use this? We have the request variable order gets tested to see if that occurs in the keys of my associative array. And if so, then use the value in the associative array, which I know that I wrote and I determined, so I know it's safe to use. It's the name of the column that corresponds to the sort order. So we've mapped the user input on the web request to something that I've hard-coded, which is the name of a column. Which also gives me an opportunity to make the code in the web request not be literally the name of the column. I can use anything I want. And you saw that very similarly in the direction case, I didn't say ASC or DSC, DESC, ascending and descending. I used up and down. So now the keys in my associative array can be up, down, and they map to values ascending and descending, which kind of is nice because I can abstract that away from the user. The user doesn't have to see little fragments of SQL syntax in the web request. I can make it anything I want and protect them from having to see that. And then I can, after I've done that mapping, I can then use those values and interpolate them directly into my SQL query in a simple manner like this and know that they're safe to use because they came from code that I wrote. And the moral of the story that I often tell people, or to sum up, is say, let users specify data values, don't let users specify code. Or any fragment of code, anything that would be interpolated into code. Okay, so that's my solution for making dynamic parts of your query which cannot be either escaped or parameterized. Use the whitelist. The next thing I hear people say is, I don't like to use prepared queries. Queries with parameters are slow. Here's the logic. It stands to reason, and that's the first point where you know that you're in trouble. It stands to reason that it will be slower because it involves 2 round trips from the client to the server. One to send the SQL string with the parameter placeholders in it, and the second one to make the request to execute the query with the respective values on that execution. 2 requests must be more expensive than 1. So I did some timings with MySQL and PHP. And you know PHP has 3 different APIs for using MySQL. MySQL, MySQLi, and PDO MySQL. And the latter 2 also support prepared queries. The first one does not. So in this case, I have all those different cases, the plain MySQL API, MySQLi without using prepared queries, but just executing the query as an immediate execution, versus preparing the query and then subsequently executing it with parameter values, and similarly with PDO. The gold bars indicate the profiled execution according to set profiler in the MySQL engine and measuring milliseconds. The blue bars indicate the elapsed time. I started a timer running in my PHP script, prepare, execute, stop timer. So you can see that there's quite a bit of overhead, but it doesn't come from SQL, nor MySQL. It comes from the overhead of the PHP language itself, executing a few functions to bind variables into those prepared queries and so on. But also notice, comparing the direct execute versus the prepared execute, the second, third, and fourth, fifth columns, you can see that using a prepared query, the execution time actually goes down slightly, but it's actually not a big problem for the RDBMS to prepare and execute a query. Or even if it was equal, or even if it was a little bit higher, it certainly kind of blows a hole in the argument that prepared queries are so slow that I don't want to use them. So this was a timer with a very, very simple query. It was just fetch me one row. I'm specifying the primary key value, and I just want to get that. It's about the fastest query you can run. Okay, so simple query with a minimal amount of overhead in the RDBMS layer shows the delta between the what the database has to do in terms of work versus the PHP application layer to the greatest degree possible. But what if the query is actually a bit more complex? So it actually takes more time to do some sorting and joining and doing other sort of complex things on the server side. Then the delta between the executing the SQL in the RDBMS versus the amount of time elapsed in the application is almost imperceptible. And both between the server side versus client side and between prepared versus direct execution. But all this is really meant to only show that it should not be your criterion that prepared queries have a lot of overhead and thus decide not to use them. Their overhead is not that bad and the benefits are great. Okay, so myths and fallacies. I covered 12 myths and fallacies and tried to explain that some of them have a grain of truth but lead you to wrong conclusions. But there's one other issue that I've added to this presentation recently, which is the assertion that no SQL databases are immune to SQL injection. Can't happen. We're not sending SQL, we're sending JavaScript MapReduce functions or whatever. And this is, in a way, true. It's sort of true by tautology. If it doesn't support SQL at all, then clearly you can't execute illicit SQL. But that's kind of cutting off your nose to spite your face, or treating a stubbed toe by cutting off your leg. So here's just sort of a mocked-up version application executing a mapping function in JavaScript with MongoDB from PHP, and we submit the mapping function written in JavaScript as a string. This is the way you execute a mapping function from PHP in MongoDB. You concoct a string. What happens if the mapping function itself needs to be dynamic based on user input? Well, you interpolate some stuff into that JavaScript function. That's your code injection. SQL injection is a special case of a broader problem called code injection, where you're allowing untrusted input to become part of code which you then execute. It's the old problem that has existed forever with functions like eval or system. If you aren't careful about what you execute, now you're executing on your server with the privileges of the process on your server. And if you allow untrusted input, you can get yourself into trouble. So any time you are executing code with a partial input from an untrusted source, it's an example of code injection. And while it isn't SQL injection, it's still dangerous. This was brought to light by a blog that came out recently, just in September. A fellow reported that he had analyzed a popular Ruby on Rails application that showed some cases of no SQL injection in an open source project. So if you're interested in seeing the nitty-gritty on this, I'll let you follow that link once you download my slides. Thanks very much for listening to my talk. This is one of the chapters in my book is about SQL injection. And thanks very much. SlideShare.net, Bill Karwin.